So recall G mod H, where G is a group, H is a subgroup. G mod H is the set of left cosets of H. And if G and H are finite, in other words, they don't have an infinite number of elements, but they have a finite number of elements, then the size or order of G mod H is the size of G divided by the size of H. And the reason is because the cosets of H partition or divide up G evenly into pieces of equal size. And so the number of cosets in this picture, for example, there's 3 cosets. So G mod H will just have 3 elements. And the number of cosets is the size of the total number of elements in G divided by the total number of elements in any one of these cosets, because these cosets have equal size or cardinality, and that size is the size or order of H. Let's do some exercises from the section 14 on factor groups. So problem number 2 says, find the order, which again just means size, of this factor group Z4 times Z12 mod 2 cross 2, the subgroup generated by 2 and the subgroup generated by 2. So what does this mean? So our group G, the big group, is Z mod 4 times Z mod 12. H is a subgroup generated by 2 and 2, which I'll explain in a second. Z4 is just the numbers 0, 1, 2, 3. The group operation is addition. Similarly, Z12 is 0 through 11. Group operation is addition. Now, the subgroup generated by 2 over here is the subgroup in Z4 that's generated by 2. And so we just take the multiples of 2, 2, 4, 6, 8, but we're in mod 4 land, and so 4 is the same as 0. So the 2, 4, 6, 8 just becomes 2, 0, 2, 0, and so forth. So the subgroup generated by 2 is just 0 and 2. It has 2 elements. Meanwhile, in Z12, the subgroup generated by 2 is something completely different. It's 2, 4, 6, 8, 10, and then once you get to 12, 12 is the same as 0 in Z mod 12. And so this is what the subgroup generated by 2 in Z12 is. It's got these 6 elements. So even though these two groups are generated by the element 2, the notation means that these are generated in these different subgroups, Z4 and Z12. So these are completely different groups. Okay, now let's consider what the product is. So with G, which is Z4 cross Z12, the product, remember, means just ordered pairs. It does not mean multiplying any numbers. No. So Z4 cross Z12 is you pick the first number from 0, 1, 2, 3, the second number from 0 through 11, and here I've just written 0 as 2 of the elements, but this has 4 times 12, or 48 elements, because there's 4 choices for the first number and 12 choices for the second number, so G has 48 elements. And H has 2 times 6, or 12 elements, because what is G? It's the direct product of these 2 subgroups. So that means the first element or component of your ordered pair can come from 0 or 2. The second component can come from any one of these 6 numbers. Here I've only written some of the choices, not all 12 elements, but 0, 4 takes 0 from here and 4 from here. Okay, so we get 12 elements. And so then G mod H has the order of G divided by the order of H, so 48 over 12, or 4 elements. So that's our answer to this question. Find the order or size of this group. It's 4. And, well, you might be wondering, what are the 4 elements? Well, turns out that there's 0, 0 plus H. This is a coset. Remember, this group is the set of cosets of H. And so a coset of H is you're adding to H some element of the group G. And these are the 4 cosets. Now, why are these the 4 possible distinct cosets? And that's because, well, for example, 1, 1 plus h is the set consisting, or the coset consisting of all the ordered pairs in G that are an odd number comma an odd number. Similarly, 0, 0 is the 0, 0 plus h are the numbers or elements in G that are consist of an even number and an even number. 1, 0 is the number elements in G that consists of an odd number followed by an even number, and so on. Okay, problem 4 is similar. It says find the order of Z3 times Z4, Z5 mod this subgroup. So Z3 cross Z5, that has 15 elements, 3 times 5. And the number of elements here is, there's only a single element in this first factor and 5 elements here. So 1 times 5 is 5. So 15 divided by 5 is 3. So there's 3 elements. You might be wondering, what are those 3 elements? And I'll leave it that as an exercise. Okay, problem number 6 says, find the order, again size, of this factor group here, where our original group is Z12 cross Z18, and the subgroup we're modding out by is the group generated by the element 4, 3. So one thing to notice is that this problem is different from the previous two, in that the group generated by 4, 3, the subgroup generated by 4, 3, is not equal to the subgroup generated by 4 cross the subgroup generated by 3. Why is that? Well, let's see what these two subgroups are. So on the right, that's the one we've seen in the previous two examples. The subgroup generated by 4 in Z12 is the multiples of 4. So 0, 4, 8, 12, but 12 is the same as 0 in mod 12 land. So that's the subgroup generated by 4. The subgroup generated by 3, this time we're in mod 18 land because the 3 is a second factor, and so it corresponds to the Z mod 18. So 0, 3, 6, 9, blah, blah, 15, and then there's 18, and then 18 is the same as 0 in mod 18 land. So, okay, so this group on the right here, the subgroup, has 3 times 6, because there's 3 choices for the first and 6 choices for the second component, and so a total of 18 elements. How many elements does this group have? It's not 18, it's going to turn out to be 6. Why? Well, let's just list naively the elements of this subgroup generated by 4, 3. The subgroup generated by an element means you start with that element and just keep adding, in this case, to that element to itself until you get back the identity. Or if you don't get back the identity, which can happen if you're in an infinite group, then you also have to add in the inverses, or in this case, negatives. But okay, so we start with 4, 3, and then add 4, 3 to itself. So that's 8, 6, because addition, or the group operation in the product group, is done component-wise. So we do 4 plus 4, that's 8, 3 plus 3, that's 6, and then we repeat that process. Add 4 plus 3 to this pair, so 4 plus 8 is 12, and 3 plus 6 is 9. Because we're in mod 12 land on the first factor, the 12 is the same as 0, so the element we get can also be in 0, 9, and so on. So we eventually hit 0, 0 after 6 attempts, or 6 adding 4, 3 to itself 6 times. So that's why this group, the subgroup generated by 4, 3, has size 6. And that size then is different from this other group, 18, which has size 18. Now, how to figure out this number 6 without listing all these elements? We've seen how to do that when we were talking about abelian groups. The order of 4, 3 is in this group is the least common multiple of the order of 4 in Z12, so that's what I've written here, and the order of 3 in Z18. And how to find these orders? Well, okay, the order of 4 in Z12, you can just think about that quickly, like 4 plus 4 plus 4 is 12, and that's 0, so it's 3. The order of 3 in Z18 is 6. Now there was you could just add 3 to itself a bunch of times and get 6. Another way to do that is this formula, or from the section on abelian groups, that the order of A in Z mod n is n divided by the GCD of A and n. So the order of 3 in 18 is 18 divided by the GCD of 3 in 18, which is 3. So 18 divided by 3 is 6. Okay, anyway, the answer to the problem, again, was we take the size of the big group, which was 12 times 18, and then we divide by the size of the subgroup. Our subgroup has size 6, so divide that by 6 and we get our answer. There's 36 elements in this factor group out here. I want to continue doing some more examples about these factor groups because they are very challenging. Again, this is the most conceptually challenging section in the course, and if you're still struggling with it, don't worry, you can just skip to the next section and things will get easier, actually. Problem 10 says, give the order of the element 26 plus the subgroup generated by 12 in the factor group Z60 mod the subgroup generated by 12. So I'll give two solutions. The first one is a bit simpler. What we're trying to figure out is how many times do we need to add 26 to itself to land in the 0 of this group. That's what order means, order of an element. How many times do you have to add, or if you're talking multiplicatively, multiply an element with itself, how many times to get back to the identity element? Well, in this group, the identity element is the subgroup generated by 12. It's not 0. It's not exactly 0. It's the subgroup generated by 12. That's because in a group G mod H, the identity element is the coset H. So we're asked how many times do we need to add 26 to itself to land in the subgroup generated by 12. So in other words, what's the smallest positive integer n such that 26n is 0 mod 12? So take a moment to think about that. That's what this question translates to. Now once we have this translation down, then it's a bit simpler. What we need to happen for 26n to be congruent to 0 mod 12 means when you take 26n divided by 12, you get an integer. Now 26n over 12 is dividing the factors of 2 in the numerator and denominator, 13n over 6, so we want this to be an integer. And so since the GCD of 13 and 6 is 1, there's no cancellation, that we can't further reduce 13 and 6, and so what we conclude is that n over 6 has to be an integer, and so that means n is 6, so that's our answer. So that was fairly quick. Here's a more complicated or conceptual solution, and I do this just to get more practice figuring out or understanding what are all these factor groups. Okay, so the subgroup generated by 12 in Z60 is, okay, you just take the multiples of 12, 12, 24, 36, 48. The next one would be 60, but 60 is 0 in mod 60 land, so we get 0. Okay, so this is the subgroup generated by 12. And so Z60 mod the subgroup generated by 12 has 60 divided by 5 elements, which is 12. Why? Because, okay, Z60 has 60 elements, and here's 5 elements that we're modding out by, and so we have a group with 12 elements. And this group is cyclic because Z60 is cyclic. Z60 is generated by 1, and so this group here is going to be generated by the coset 1 plus subgroup generated by 12. And so with that one, in other words, more concretely, Z60 mod the subgroup generated by 12 consists of 0, the coset 0 plus 12, 1 plus 12, 2 plus 12, and so on, all the way up to 11 plus 12. Because once you go to 12 plus 12, you're back in this coset here. And again, what's a little bit confusing about these factor groups is that this element here, 0 plus bracket 12, it's considered as a single thing in this group, single element. But if you look into what is 0 plus 12, bracket 12, this is actually the set of these numbers here. Set of multiples of 12, but then we're also in mod 60 land, so it's the set of 5 elements. So it's a little bit conceptually taxing and just takes getting used to. Most of the course won't involve this at all, actually, so don't worry too much if it feels very confusing. It is. Okay, and so pictorially, what's going on? So we start with Z60. That's the numbers from 0 to 59. Addition is a group operation. And in there we have this number 26 that we're interested in finding the order of 26. Okay, and then we mod out by the subgroup generated by 12. And then we've seen that the resulting group has 11 elements. 12 elements. I didn't list out in here all 12, but I listed them up here. It's 0 through 11, so there's one more than 11, so there's 12 elements. Okay. All right, and so this 26, it's 2 more than a multiple of 12, so it maps to the coset 2 plus bracket 12. And then Z mod 60 modulo 12 is a cyclic group of order 12, and that's what Z12 is. And so under this map from Z mod 60 mod 12 to Z mod 12, the 1 plus 12 goes to 1. That's how I'm defining this map. And so that would mean that 2 plus 12 goes to 2 and so forth. So yeah, so this 26 goes to the coset 26 plus bracket 12, which is the same as the coset 2 plus bracket 12. That's what I was trying to explain actually in the green lines here. That 1 goes to this coset 1 plus bracket 12, but 13 also goes to the coset 1 plus bracket 12. And okay, so the question reduces to find the order of 2 in Z12, because 26 goes to this coset, which goes to 2. And so we need to find the order of 2 in Z12, because the question was asking, find the order of this coset 26, which is the same as 2 mod 12, 26 plus 12 in this group here. So the question reduces to finding the order of 2 in Z12, and that's the formula we had from a while back. And that formula gives you 6. Again, this is much more complicated than necessary, so I may be regretting covering this, but it is what it is. Okay, let's do problem 12 that says give the order of this element 3, 1 plus this subgroup. So this here is a coset. It's an element of this factor group. Again, so it's very conceptually challenging because there's so many numbers floating around essentially. So let's see what's this picture as a picture what's going on. So we start with this big group, Z4 cross Z4. And that has 16 elements. Because Z4 consists of the numbers 0, 1, 2, 3. This other Z4 has those same 4 numbers. So, and then Z4 cross Z4 is the ordered pairs. So I've written 4 of them down here, but there's a total of 16. And so this group G, Z4 cross Z4, has 16 elements. Then what is the subgroup generated by 1, 1? It's 1, 1 plus 1, 1, which is 2, 2. Add 1, 1 to that, you get 3, 3. Add 1, 1 to 3, 3, you get 4, 4. But in Z4 cross Z4, 4, 4 is the same as 0. So this here is a subgroup generated by 1, 1. It has just these 4 elements. And when we quotient out or mod out or form the factor group, all these elements are like squished to 0, or the identity element, or a single element. So that's what I'm depicting here. And the 3, 1 is somewhere out here. It's not in H, because H consists of these 4 ordered pairs. 3, 1 is not in them. And so the coset 3 plus 3, 1 plus H is somewhere here. It's not this identity element. Okay. And the question is find the order of this element. So order of an element means how many times you have to add that element to itself to get the identity element. Okay, let's just add 3, 1 to itself in the quotient group just once. Okay, or twice, whatever. 3 comma 1 plus 3 comma 1, the definition of the group operation in the factor group is you just add their representatives. So 3 comma 1 plus 3 comma 1 is 6 comma 2, and then here's the associated coset. You just tack on the plus h. And then because 6 comma 2 is the same as 2 comma 2 in this group z4 cross z4, that's what I've done next. 6 is the same as 2 mod 4. Okay, and let's just, to make things concrete, what is this coset? Let's just list all the elements. Well, 2 comma 2 plus the set of elements that are what h is, and then I add 2 comma 2 to each of these, and so I get 2 comma 2, 3 comma 3, and so forth. And then I get back h. So the order is 2, because we added 3 comma 1 to itself 2 times, here and here, to get back the identity element in the factor group, which is, when if the factor group is G mod h, the identity element is h. Finally, let's do a problem that's more proof-oriented instead of with actual numbers. Okay, so the hypothesis or the assumption is let H be a normal subgroup of G. The important fact then is that G mod H is a group. Okay, and assume that the size of G mod H is M. Show that G to the M is an element of H for all elements of the group. Okay, so for the proof, since H is normal, G mod H is a group. It's going to be a group of size M, is what we're told. And if you have a group of size M, then if you take any element of that group and raise it to the mth power, you'll get the identity element. That's some consequence of Lagrange's theorem, or consequences of how the cosets partition a group. So in particular, GH is an element of this factor group or quotient group. And so if I take this coset GH and raise it to the mth power, I'll get the coset H, because H is the identity element of this factor group. And you can hear I've written down what I've just said, because in a group of size M, any element raised to the mth power is the identity element. And that's again because the order of an element divides M because of Lagrange's theorem. Okay, so now what is GH to the mth power? The definition of product in the factor group is you take the representative, in this case G, and multiply it, in this case to multiply M times with itself, and so we get G to the M then times H. Okay, and so what we know is that this coset G to the M times H is equal to the coset H, and that means that G to the M is in H, because you can just take the identity element in the subgroup H, and that G to the M times the identity element will be in H. So that finishes the proof that G to the M is in H.